from heterogeneous systems to challenges of future programming models, because I figured that was more relevant to this session. Given that heterogeneous systems have basically taken over the top 10, with 5 of the top 10 systems being accelerated systems. I think I just turned this thing off, did I? No. With 5 of the top 10 being accelerated systems, I thought this would be a more relevant topic. Just a few words. I'm the group leader of applied computer science, and the charge of my group is to look at
forward, backwards, and bottom, please.
Awesome. Thank you. What my group does is look at technology that's coming maybe 5-10 years in the future, and trying to identify how we might leverage it to get LANL's mission done. One of the unique challenges we have at LANL is that we have a large base of Fortran users and a large set of legacy Fortran codes that we need to make sure that we carry along into the future. This raises some unique challenges, and I was heartened to see in the IDC report that over 80% of the high-performance codes were Fortran-based. So these challenges, I believe, are shared by all. There's a number of people that have contributed to this talk on the different aspects of it. And is it okay if I turn this off? I mean, I think I talk loud enough that I'm not sure I need it. Can people hear me in the back? Okay. So there's a number of people that have contributed to this talk, and not all the slides are mine, and so I may not be able to answer all your questions precisely, but I can point you at the right person to answer this. Okay. So we've already seen a lot of the anticipated changes in computer architecture. I'll just point out a few trends. You'll see echoes of a number of talks from yesterday and from Pete's talk this morning in my talk. These are topics that are important that we need to address, and we're not entirely sure how we will. But no matter how we address this, we have to come up with a new programming model for extracting all the parallelism we can get from within a node. So, and I'll try to point out what the difference between the current and evolving programming models are. And I'll look at a few front runners in this respect, and just try and point out their advantages and disadvantages as far as existing code bases and new code bases are concerned. So over the past couple decades, computer architecture hasn't really changed from a programmer point of view. That is, the topology of the machine has stayed the same. You have the CPU, you have memory, you have I/O, and that's all that the programmer needed to know. All the speed up has come from basically increasing the clock speed and increasing the complexity of the chip, like say by adding hardware caches, adding more pipelines. You know, you get every 2 years you get a faster, every 6 months you get a faster CPU. And with clusters, I mean, you just keep adding more nodes. But in spite of all of this, all the programmer needed to do to keep their codes up to date was recompile. And typically, recompiling was enough to reap the benefits, but you never got the entire benefit of the new platform. That is, if the chip got twice as fast, you might get maybe 10% of that increase in your code. But it was still faster, and the wall clock time to solve things went down. And again, I mean, as Pete pointed out, this trend is unsustainable. That is, that you just keep adding more complexity, keep adding more pipelines, and a large reason for that is power. And transferring data across the chip is expensive. I mean, it is estimated that 50% of the power for an exascale machine will come from the memory movement alone. And so we need new algorithms that maximize the locality of the data you're working on and maximize how much you reuse the data. And this is not anything new. This has been true for quite some time. All the leading edge codes have known this for a while, and they have architecture-specific algorithms that make use of the specific features of different chips and the locality. But as we go forward, as the parallelism within a node balloons, this is going to become more and more important to the point where you will not be able to do your work the way you have typically been doing. And the way we believe parallelism within a node will increase is through wider vector widths. I mean, we have SSE vectors right now that are about 2 wide in double precision. These, you saw the 16 flops in Pete's slide. That's 8 wide double precision, assuming that they are multiply adds. You'll see more threads per core. You'll see more simpler cores per CPU. And at least in the short term, you're likely to see a large number of heterogeneous systems until the manufacturers actually start pulling these into the chip. And effectively what this does is that it kills the recompile and run strategy that we've been using for 20 years and grown used to. And we have to effectively rewrite our codes if we want to continue forward. And one point which hasn't really been beaten on this far are the fault rates are expected to increase just because of the increased level of concurrency within a chip. And we have to find some means of dealing with resilience or lack thereof. And just a quick look at the market, I mean, as to see just who's driving this. If you look at the market from 2008 and 2009, the video game market was 39 billion. The 2009 video game market was 60 billion. Netbooks were 9 billion in 2009. And in 2010, between April 2010 and April 2011, Apple sold 14 million iPad 1s. At $500 for the cheapest one, that's a $7 billion market. NNSA's budget for supercomputers is 0.2 billion. And so when you get a new crop of developers, and someone touched on this yesterday, they're not really going to focus on NNSA or Office of Science or any of the high supercomputing markets. What they're going to see is they're going to see the game market exploding, they're going to see the embedded market exploding, and they're going to be typically drawn to that. And that may not entirely be a bad thing, because the platforms those games are running on are inherently heterogeneous, they are inherently parallel, and so these new developers, even though they have not had formal MPI training, have been playing with CUDA, they've been playing with OpenCL, they've already started thinking about how are we going to use this to make my game faster. And and I think that will help us as we go forward in recruiting the right kinds of people that have already started thinking about running things in parallel and extracting the maximum they can out of a heterogeneous system. But the other side of this is that this leads to very interesting trade-offs in the power, performance, and memory space. These are things which Pete alluded to earlier as well. So about a year ago or so, there were 2 distinct swim lanes. And there was the many-core swim lane, which was Intel, IBM, Sun, and so on, which are the traditional CPU manufacturers. And these were expected to be of the order of 1,000 threads per socket. On the other side, there was the accelerated or hybrid swim lane. I mean, this was one that was brought to the forefront by Roadrunner, which was the world's first petaflop computer, and it was an accelerated hybrid computer with many different kinds of chips in it. And the compute sat apart from the network. So if you wanted to get 96% of the compute was in the cell processor, and if you wanted to communicate with your neighboring nodes, you had to actually go down to the Xeon over the PCI bus, communicate with your neighbors, get the data, and push it back up over the PCI bus. And it's effectively how the GPU clusters work today. As this progresses, we expect that we are going to see more and more of the heterogeneity being pulled into the chip. For example, AMD's Fusion device and NVIDIA's Denver project are examples of these. But what sets these apart is that these likely have of the order of 100,000 threads per socket, if you really want to extract all the concurrency out of it. So, but as we go forward, I mean, these lines are starting to get blurred between the two swim lanes. You see NVIDIA talking about adding ARM chips to their GPUs. The interesting thing about ARM chips is that they have said they will run Windows 8 natively. So in essence, the GPU could host the operating system. There's the AMD's Fusion platform and Intel's Mic platform, which is what they're moving to over the next few decades. The Mic has 32 to 128 cores, and at least the first two announced architectures attached to the host over a PCI bus and need a Xeon to drive them, which is why I put them in the accelerated streaming category. But irrespective of all of this, the common theme here is the increased intranode task parallelism, without which you cannot really extract all the power from these machines. And there's the data parallelism. The way most of these chips get a lot of their power is through SIMD operations, which is single instruction multiple data. And they run, for example, if you were to take the cell processor on the SPU, it runs 2 floating point operations at one shot on a vector. The Intel chips run the same number of floating points. The SIMD vectors are 128-bit long. So you run either 2 64-bit or 4 16-bit operations, 4 32-bit operations. But the point is that what you're going to see is that you're going to see the SIMD vector lengths increase dramatically. And from our experience with Roadrunner, we found that the existing algorithms have a tough time dealing with the increased SIMD lengths. Even at 2, it was challenging to extract the full power of Roadrunner out of it. And we expect that as we go into the future, this is going to get tougher. I'm going to really skip through these. Basically, Maxwell will be likely the first released Denver product. And it's similar to Echelon, which is their, I believe, their UHPC entry, which had 128 streaming processors and 8 latency processors. And the latency processors are basically things like the ARM core, which can help you deal with memory latency and corral memory for you. AMD Fusion, we saw some of this yesterday, where you have the CPU cores and the GPU cores sitting on the same chip. Currently, they do not have coherent memory, but we saw AMD's plans for the future during, I believe, just after lunch yesterday, where they said that eventually they will have coherent memory. And basically, there's a lot of heterogeneity within the same chip, and similar to the cell processor from IBM. And there's Intel's Mic, which is different from these two in the sense that it is made up of a large number of simpler x86 cores. And each of these 3 platforms, each of these manufacturers has been pushing their own programming model forward. And what I'm going to do next is just touch on the different programming models from a Fortran programmer's point of view, and just see how you would express a simple program in all of these, and see what the barriers to adoption might be and what problems they have. So just to motivate the topic, right? Any new programming model that we have needs to expose the added concurrency, which means that you got to expose the vectors in a way that programmers are able to use it. You have to expose the threads in a way that programmers are able to use it. You have to find some way to let the programmer know about the memory and the CPU hierarchy. And this one is extremely important. You have to enable performance portability. OpenCL enables performance, but it's not quite portable. In the sense of, if you want performance on every device, you have to write a kernel for that specific device. CUDA claims to be performance portable across all NVIDIA devices. However, if you have a Compute 1.0 device and a Compute 3.0 device, you need to write a separate driver for each of them, or you need to partition your memory differently. So we are not really all the way there yet. OpenMP, the next, actually it's just been released about a month ago, of OpenMP promises some more advances in this. But this is extremely important as we go forward, because no application developer will be willing to rewrite their code twice in a short period of time. They may be willing to rewrite it once, but they're not going to be willing to rewrite it every time for every new architecture that comes out. And so finding the right balance between how much rewrite has to be done, how much abstraction there is, becomes extremely important. And this last topic is very important, which is we need to expose different compiler metrics. Because especially going into the exascale era, you may not be compiling for maximum speed. You may be compiling for some power envelope that you specify. And so the compiler may give you an executable that turns off pieces of the chip, turns off pieces of the network, depending on what your application specifies, so that you stay under some power budget. This is not how we are used to thinking about computers and about programs in general. That it's always been, well, let's minimize the number of flops that we have because memory is cheap and everything else just falls in place. As we go forward, we're going from a flops is expensive, memory is cheap, to memory is really, really expensive, flops are extremely cheap paradigm. And so if you can recompute something, the compiler may recompute it rather than storing it. But it's going to need help from the developers, and we need to expose these. All right, so this is a simple element-wise array addition that I have presented a reference code. It's written in C, but it's said that a talented Fortran programmer can write Fortran in any language. And this is an embodiment of that. So all we are doing is we're taking some big array and adding A and B, assigning it to C, and moving on. And I just wanted to explore how this would be done under different programming paradigms that different companies are pushing forth. Now, OpenMP is the first one that I picked up. It's very seductive because the intrusiveness on the structure of your code, not the code itself, but the structure of your code, is very little. All you do is sprinkle a few pragmas here and there in your code. And for example, here it says that this bottom for loop is, can be executed in parallel, and then you do that. It does have more advanced constructs, but for someone that's moving into this for the first time, this is how a starting OpenMP person may do it. Right? Once you become an expert, you learn better ways of doing this. The problem with OpenMP is that you have to do this now for every single loop in your code, and if you have a complex application, that's painful, and it makes the source code much worse looking than when you started out. It's very difficult to maintain this. You really don't want a programmer going in and stating this. You'd rather have the programmer state what they want to do almost than how they want the computer to do it, which is how we have grown used to thinking about things. Although with the HMPP and CAPS, they now have accelerator-friendly OpenMP. PGI is talking about a Fortran that will do OpenMP that can then send things to an accelerator. So the part about not being accelerator-friendly is no longer true. But as you can see, I mean, you show this to a programmer, it says, oh, that is cool. I just put that in and I'm done. I get all the parallelism in the node, except it's not entirely true. Okay, OpenCL. The nice thing about OpenCL is that it gives you a lot of portability. And I apologize for the small print here, but I was trying to get everything that was needed to get that same loop running under OpenCL on multiple devices into a box that fits on the screen. At the top here on these two kernels is the actual addition being done. The rest of these lines here are setup, where you're allocating memory on different devices. In principle, this is something that you should hide away behind an abstraction layer, right? But most people don't. And most people have the memory allocations for device memory in line. And these last two lines here basically say, well, run this on the kernel and run this kernel on the accelerator and get back my results. The other problem with this is that it requires re-architecting your entire code. You have to start thinking about what the data flow is, and you have to think really hard about what the data flow is so that you can extract all the parallelism you can out of it. And it does require cumbersome setup and shutdown of host and accelerator elements, but you pay that cost one time. I mean, the first time you write an OpenCL code, you pay that cost, and then if you're smart, you reuse those lines in every other code that you write. NVIDIA does a better job of marketing. When they do this, all they show is they say, hey, look, this is all that you have to do to run this in CUDA. But similar to OpenMP, you do have to allocate device memory and host memory separately, put it on the device, do the compute, get the result back, and so on. So let me just go back to one of the problems with OpenCL as I see it. The big advantage of OpenCL that's always started is that it's an open standard. And LANL, in fact, has a member on the Kronos committee. But I would say that's also OpenCL's biggest, whoa, only 4 minutes left. All right, I'm going to start talking faster, people. Is that one of its biggest disadvantages is the same thing, because you also have to satisfy the embedded market. It's not about HPC. It's the number of people from the embedded market on that committee is huge. There are cell phone makers, there are people making tiny boxes. All of those, they all want to support OpenCL, and they all have a vote that's equal. So it makes it very difficult to get HPC-specific instructions into the standard. CUDA doesn't have that disadvantage. It's under a single vendor control, so they can change it very quickly. It's just extensions to C and C++. The problem is that it works only with NVIDIA GPUs. And if for whatever reason NVIDIA disappears tomorrow, your investment in CUDA is going to be wasted. That said, there are two ways to use CUDA. There's a driver API and a user API, and if you were to use the driver API, it's essentially analogous to OpenCL. Intel has a different take on this. What they say is that they have something that's based on Silk Plus, and it's C++ template based, and I'm just going to bring this up real quick. If you're a C++ programmer, this is very clean, but try explaining this to a Fortran programmer. It's extremely difficult getting that across. But essentially, it's a very nice abstraction of the threads. It's a nice abstraction of the data parallelism. And once you get into the mode of thinking, it really works well. Doesn't work on GPUs yet. Also, like CUDA and like OpenCL, it requires re-architecting your code. So the other side of this coin is to say, all right, well, I could write specifically for every architecture, or I could create a DSL that's like a data parallel DSL. The one we like to use at LANL is called Scout. And this is a data parallel DSL that targets OpenCL, it targets CUDA. Basically, it spits out LLVM at the other end. And what you do is, it's designed to sit on a mesh, so you define a mesh, and you just say simple things like, for all cells of my mesh, do this operation. You don't specify the indices or the order in which it's done. Again, it's a research tool chain, so it's excellent for exploring hybrid computing, but its disadvantage as well is that it's a research tool chain, so if the main researcher goes away, so goes Scout. And finally, you have to rewrite the entire code as with the other ones, and that's the continuing theme. I did drop in functional programming in here. I don't expect this will go very far with the HPC community, but I think this is something worth exploring. And the slides are available on the website, so I'm going to kind of zip through this because I want to get to resilience. As we go towards exascale, the number of faults is going to increase dramatically. And the worrying point is that at about 20 nanometers, there are reports that show errors in logic units. and that were equal to the memory rates at 100 nanometers. And if we, oh, good Lord, okay. And we have to use, basically we will be using that, and one of the ideas that has been thrown around is that we can use tunable fidelity. That is, you tell the computer where you want to run things, where you care about the results, and other cases where you don't care as much, so you can tune the resilience up or down. Your performance will vary based on that. And there are some experimental tools that are available to explore such environments. So finally, but just one last point on resiliency is, even though it seems now that resiliency is extremely important, I believe all hardware manufacturers have a great sense of pride in their product. They will not put something out the door that is not usable. And so even though this may be important, it may not be as important as we think it is today. And I'm just going to let you read that because I'm out of time. So thank you.